How does that look for everybody at home? I'm going to take the silence to mean it looks great. All right, cool. So, last class, we left off talking about the quotient rule. The quotient rule, we said we could remember using a mnemonic, low d high minus high d low, all over the square of what's below, right? Just a useful tool. And then we applied it to this first example here. And I showed that, hey, instead of just going right to it and saying that y prime is going to be equal to g of x times f prime of x minus f of x times g prime of x, all divided by g squared of x. Instead of going about it right to this, right, I was saying in the last class, why don't we first declare what f of x is. In this example, let's call it x1. Well, let's step back for a second. This is, of course, assuming that y is equal to f of x over g of x. So let's declare that f of x is equal to x minus 1. Then f prime of x is just equal to 1. And let's declare that g of x is equal to 2x plus 3. And g prime of x is equal to 2. Now we can just put it all together, right? We can plug in g. We can plug in f prime. We can plug in f. We can plug in g prime, so forth and so on. Agreed? It is way easier to go about structuring our problem this way than it is just to go ahead and calculate everything straight through, right? And the reason why it's easier for us is because what if we do make a mistake? Who wants to go back from this, trace back all the algebra, and then trace back all the calculus, just to identify where our mistake is? If we go about it this way, we can look at it and say, all right, our calculus is right. Yeah. And now all we have to do is identify from this point on if our algebra is right. So as a way of checking our work, keeping things organized, I would suggest an approach like this as opposed to like that. Cool? So having said that, I'd like you all to give this problem a shot. But before you do, remember the tangent line to h of x at x equals some number is y minus h evaluated at that number equal to the derivative of h of x at that number times x minus that number. I'd like y'all to try this on your own really quick. Put all of this together. So it takes a couple minutes, doesn't it? It's not a quick problem. So looking at what we're trying to do in this problem, we're trying to find this line, right? This tangent line right here, the gray one. So the first thing we're going to want to do is calculate what our derivative actually is. I'm doing that quickly. We move all the way through and get to this final point, right? So from here, we're just going to plug in 1, because that's going to give us the slope of our tangent line when x is equal to 1, right? From our original equation, we know what our y is. It's -1. So from all of this, we just throw it all together now. We get our answer. Is everybody cool with this? So what are we doing in totality, step by step? The first thing we're doing is we're saying y is equal to f of x over g of x f of x is equal to 2x squared minus 4x plus 3 the derivative of f of x is going to be 4x minus 4 g of x, that's our denominator, so it's 2 minus 3x. It's going to have a derivative of -3. So putting all of this together now, y prime is going to equal high d low or low d high, which is first? Low d high, right? So the first term of our numerator is going to be 2 minus 3x times the derivative of our numerator, which is 4x minus 4, minus our original numerator, the quantity 2x squared minus 4x plus 3, that quantity times negative 3, all divided by our original denominator squared, 2 minus 3x, that thing squared. Just what they've got, right? First term, 2 minus 3x, that quantity times 4x minus 4, minus 2x squared minus 4x plus 3, that quantity times negative 3. And then in our denominator, 2 minus 3x squared. Now from here, we're going to want to simplify it as much as we can. And since I don't want to go through the algebra and waste everybody's time doing that, I'm just going to copy it right off the board over here. Because we've all got better things to do with our time than watch me do algebra. Negative 6x squared plus 8x plus 1, all divided by 2 minus 3x, that quantity squared. Now, and then to find the slope, we're evaluating the derivative at x equal to 1, right? So we're just going to want to plug in 1 wherever we see this x. So we're going to get negative 6 times 1 squared plus 8 times 1 plus 1, all divided by 2 minus 3 times 1, that quantity squared. Is everybody cool with this? Yeah. So looking at this, we should get 3. Now, presumably, we've already evaluated our original function at 1. Cool? Because all we're doing here is we're plugging in x into our original equation and saying, what do we get when x is equal to 1? Well, it's going to come out to be negative 1. Conveniently, they went ahead and did that for us. So this is going to be our x naught and our y naught, right? So now we've got everything we need to find the equation of this line. This line is going to be y minus negative 1 is equal to 3 times the quantity x minus 1. Well, minus negative 1, we can drop these parentheses and make this addition, right? Yeah. Can distribute this 3 through. We're going to get 3x minus 3. Subtract the 1 from both sides. Y is equal to 3x minus 4. Now, all we've done here is calculated the derivative. We found out what it was, right? Then we calculated it at our particular x value. That gave us the 3. Then we said, all right, this is going to be the slope in our point slope formula. In the original point, whenever x is equal to 1, this is going to be our x naught and our y naught in our point slope formula. That's all we've done here, right? And using all of that information, we were able to find the tangent line. Does this make sense what I mean? No? Dope. So, having said that, what about this one? We have a fraction and a fraction. It's fractionception. I know, right? I'm so good with these dad jokes. What are we going to do for this? Well, the first thing we're going to want to do is we're going to want to rewrite all of this. What's funny is like I've got dad jokes for days and I don't even have a kid. My girlfriend thinks I'm just trying to see how long I can survive without her killing me. That's where we're at now, is trying to figure out if I'm doing it because I think I'm funny or if I'm doing it to drive her crazy. So, first thing, like I said, we're going to want to rewrite this. We've got 3 minus 1 over x in our numerator and x plus 5 in our denominator. The way I would rewrite this is just me myself. I would rewrite this in terms of powers, just because it helps us see what's going on later down the road. All right, so this is our y value. Given this, now we know what our f and our g are, right? We know what our numerator and our denominator can be rewritten as. F of x, I rewrite this as 3 minus x to the negative first, which means the derivative is going to be positive x to the negative second power, right? Because we're pulling down this negative 1. So rewriting all of this. F prime of x is going to be negative 1 times d dx of x to the negative first by power rule, we're going to get that this is x to the negative second power. So moving on now to g of x, that's going to be x plus 5, and g prime of x is just going to be 1. So from here, we're just going to combine everything again, right? Y prime is going to be equal to g of x times f prime of x minus f of x g prime of x divided by g squared of x. Yeah? So really, we're just plugging and playing now. I did not catch that. They went a slightly different route. Huh. They went a much different route than I did. Good on them. So the way they went about this, they multiplied our numerator and our denominator by x. Because x over x is 1, right? So it's not going to change anything. Multiplying this by x over x won't change anything as far as the value is concerned. It's just going to change what our denominator, what our fraction looks like. But it's not going to change the graph or the values or anything like that. So from there, they went ahead and said, all right, now let's calculate the derivative. And moved through. They got to this final term down here. Now notice, because we didn't change that, our denominator is going to look a little bit different, and we're going to have to reorder some things. But after we do all of that, it'll come out to be equivalent. Make sense what I mean? Cool. So as some examples, notice, given these original functions, the first thing they do with all of them is they rewrite them, right? And then they differentiate, and then they simplify. This rewriting process it's not required, but it's a good idea. Like it will save you time and headaches in the future. Make sense what I mean? Cool. Okay, what about this? What are we going to do here? We're going to first start off by declaring what f and g are. F of x is going to be equal to 1 minus 2x, that quantity times the quantity 3x plus 1, or plus 2, I mean, right? G of x is going to be equal to 5x minus 4. What's the derivative of f of x? It's going to be the derivative of one of these two terms times the original term, plus the derivative of the other term times the original term, right? So what I'm saying is f prime of x is going to be equal to 1 minus 2x times, I don't have enough room on the board, d dx of 3x plus 2 plus 3x plus 2, that quantity, times d dx of 1 minus 2x, right? Because of the product rule. what we've done here is used the product rule. Which says, given a function h of x, which is equal to f of x times g of x, the derivative of h of x is going to be equal to g of x times f of x prime plus f of x times g of x prime, right? So all I've done to our numerator so far is define what that f of x is, right? Quote unquote. And then apply the product rule to find its derivative. Everybody cool with this? Yeah. All right. So what's this derivative going to be? The derivative of 1 minus 2x. Negative 2, yep. The derivative of 3x plus 2? 3. So what we're going to have is 1 minus 2x, that quantity, times 3, plus 3x plus 2, that quantity, times negative 2. Make sense? Let's rewrite this. Which we can, of course, simplify, right? Like, we can make this nice and neat. Pass everything through, get 3 minus 6x plus 6x plus negative, or my mistake, minus 6x minus 4. Reduce this the rest of the way down. Get negative 12x minus 1, right? Is everybody with me on that? Yep. Now, going back to g of x is equal to 5x minus 4. So g primed of x is just going to be 5. And now we're going to plug all of this back together. Using the quotient rule. So this is another reason why I strongly urge y'all to use this sort of breakout method, because you start looking at product rules mixed in with all these other different rules. Eventually we'll start getting out of chain rules. These can become real bastards, like, for lack of a better word. They can suck. And it can happen pretty quick. That's why I keep saying it, and I'll keep saying it. Use a method like this to organize your thoughts, and then do the algebra. Because again, I forgot a square somewhere in here. Trace this all the way back up. That's going to hurt. But at least this way you can be like, I know the calculus is right, so it's got to be an algebra mistake. Or I know the algebra is right, so it's got to be a calculus mistake. Having said that, putting everything together, this is our f prime, right? It's going to come out to be negative 12x minus 1. Our g prime is going to be right here, just this 5. We plugged everything back together and calculated it just the same. Cool. So as an example of an application, rates of changes, derivatives, show up in nursing. I'm talking about things like blood pressure. In this particular case, we're trying to figure out what the rate of change is at a particular time. The time is equal to 5. I'll let you all go through this on your own at home. But I just wanted to give you all an example of where it's used in other areas of life. Having said that, actually, a great example of where you use derivatives every day is driving. Velocity is a derivative. You go so far per time. That's a derivative by definition. So, shows up everywhere. Also, another concept check. Check them out. They're good. They're great. Section 2.5. This is where it's going to get a little hairy on derivatives. I'm not going to lie to you all about that at all. This is going to get hairy for a second. And the reason why is because things get weird fast. We've got this thing called the chain rule. What the chain rule is telling us is we've got this function, h of x, and it's going to be equal to f of g of x. F of u is going to be equal to y, and g of x is going to be equal to u. Now, when we take the derivative of h of x, what we're going to do is we're going to be taking the derivative of f of u with respect to u and multiplying it by the derivative of g of x with respect to x. Does this make sense to everybody? The chain rule is really just saying when you have a bunch of functions daisy chained together, their derivatives are going to be daisy chained together. Get what I mean? So let's look at an example. Actually, let's look at two different examples. F of x is equal to x plus 1, that quantity squared. All right, what we've got here, let me actually rewrite this as h of x to keep the notation the same. What we've got here is f of u is equal to u squared. G of x is equal to x plus 1. So, using what we just saw, the derivative of h of x is going to be equal to the derivative of f of u times g of x. Right? That's what this is saying up here. All right, so with that, the derivative of f of u is going to be equal to 2u. Oh, can't see that. I'll come back to it in a minute. And the derivative of g of x is going to be just 1. Agreed? Yeah? So, that tells us that what we're going to get when we find the derivative of h of x is going to be 2u times 1. But hey, notice something really quick. U is defined as g of x, right? If that's what we're doing, we're saying that f of g of x is all of this. Then what we're saying is that g of x has to be equal to u, and f of u has to be equal to 1. Get what I mean? Kind of, sort of. So then, knowing that, this must give us 2 times u. Well, we just said u is equal to g of x, so that's x plus 1. Or 2x plus 2. Right? All right. So we just did this using the chain rule. But check out, we can reduce all of this, right? We can simplify our original function. I'm going to keep this right here. When we expand this out, we're going to get x squared plus 2x plus 1, right? So we can just apply the derivative here. When we do, this is our power rule. Comes out to be 2 of x. This is our constant rule and our power rule, right? So this is just going to come out to be 2. This is our constant rule. which is going to come out to be 0. Comes out to be the exact same. Comes out to be the exact same answer. This will always happen. What I'm trying to get at is that if you have a problem that is ugly and nasty, we could imagine this being like a derivative, or a fraction, right? And there being something else that we have to multiply by, blah, blah, blah. The chain rule can oftentimes be used to help us make real ugly problems real easy to solve. But unfortunately, given that it has that power, it's also hard to understand sometimes. So, to explain the chain rule, a common example that's used to compare it to is rates of change. If I wanted to talk about kilometers per hour, I'm driving along, right? And my friend in the seat next to me is from the UK, I don't know, Germany, whatever. And the dude's like, yo, you're driving too fast. It's however many kilometers an hour. I look at the speedometer, I have no damn clue what that is, but I know miles per hour is what I'm driving at. If I want to find out what it is in kilometers, you would have to use a rate of change. Excuse me. We would have to use that rate of conversion, right? Well, what this is the rate of change miles per hour. And this is how fast kilometers change per mile. So really, we're talking about derivatives. But it's an example that shows up in chemistry, biology, et cetera, et cetera, et cetera. This is a common way to think of the chain rule. What we're doing is we've got this initial function, h of x, and it's equal to f of u, or f of g of x. This thing let me finish the thought. This thing is going to be f of u, right? The derivative there. This thing is going to be u prime or g of x, right? So chain rule is really just nothing more than units of conversion in some sense of the word. Does that make sense what it means to everybody? Yeah, cool. Having said that, more of the same. We can think of f of g of x as f of u. Then y prime will be the derivative of f of u times u prime. So, problems we don't need chain rule for. Voila. Bunch of basic problems we've already talked about. Problems we will. Notice all of these, we could have done in different ways, right? Like we could have calculated what 3x plus 2 to the 5th power is, but nobody wants to do that. We could have calculated this fraction expanded out. Nobody wants to do that. The first two would be hard. but there are ways to do that. But just to give you a taste of which problems you can and can't solve with chain rules. All right, so starting off looking at A, we've got 1 over x plus 1. Well, we could think of f as 1 over u, and we could think of u as x plus 1. And going about it this way, we can apply the chain rule to solve this quotient, the derivative of this quotient. Does that make sense to what I mean? Kind of, sort of? Similarly, got this radical. Same idea. So, having said that, I want you all to try this on your own. Give yourselves 2 minutes to get it done. Anybody want to volunteer their answer as tribute? So the first thing we're going to want to do is find the derivative of f of u, right? I'll come back to it in a second. First thing we're going to do is find the derivative of f of u, right? And then we're going to multiply it by the derivative of u. Or we can rewrite it as f of u g of x prime, right? Everybody agree? It'll work in a second, I hope. So if this is the case, well, f of u prime is going to be 3u squared. G prime of x is going to be two x please work. So putting it all together, I'm going to have 3 times x squared plus 1, that quantity squared, times 2 of x. That's not where I want to go. This place. Okay. So looking at all of this, 3 times x squared plus 1, it's dy du, right? Times g prime of x is du dx. And finally, we're going to get that 3x squared. Well, they went ahead and simplified it by multiplying the 2 and 3. 6x times the quantity x squared plus 1 squared. Everybody cool with this? Okay. This brings us to the general chain rule. Notice before when we talked about, the general power rule. Notice before we were talking about the power rule, but just in terms of x taken to some power. Right? The general power rule states that the derivative of u to the n is equal to n times u minus times u raised to the u or to the n minus 1 times the derivative of u with respect to x. So if we wanted to, could look back at this and say, hey, if u is equal to x, then the derivative of u with respect to x is just going to be 1. So it's the same thing, right? Does that make sense for me? Yeah. Cool. Again, same thing. Applying it now. Take the derivative of what's inside of u. That's going to give you 3 minus 4x. And the derivative of this whole thing is going to be that 3 minus 4x times lowering our power and reducing it by 1 right? Same idea. Just plug and play. Is everybody cool with this? Okay. Sweet. All right, so having said that, look at this one. We're given that y is equal to the cubed root of x squared plus 4, that quantity squared, is that correct? Yeah, awesome. Let's go ahead and rewrite this. Anytime we take a root, we're just taking 1 over that power, right? So what I'm saying is so we can rewrite everything underneath the radical as x squared plus 4 of, or we'll take it to the second power, raised to the 1 over 3 power. But we can reduce this and simplify it even further. So doing that, we get 2 over 3. So defining now f of u as u to the 2 over 3rd power and g of x as x squared plus 4 what we find is that f prime of u is going to be equal to 2 over 3 u to the negative 1/3 and g prime of x is going to be equal to 2x. So y prime is going to be 2 over 3 x squared plus 4 raised to the negative 1 over 3 times 2x. Now we want to evaluate this at x equal to 2. Plugging in 2 here, we're going to get 4. So this is 8 to the negative 1/3 power times 2 over 3 times 4, right? I'm not doing this in my head. I'm just going to write it all out. So this is going to come out to be 2 over 3 8 to the negative 1/3 power times 4. Well, the cubed root of 8 is going to be 2. So we're going to end up with 4 over 3. run through all of this. We have 4x divided by 3 times the cubed root of x squared plus 4. So far, so good, right? Like everything matches up here. What we got here. Plugging in now, 2. We're going to get that our derivative is equal to 4 over 3. Is everybody cool with this? Now we can go on to find the tangent line, same way we have in the past. $14 more minutes. All right, so the other day I said that you can use the product rule to find the quotient rule. Today I'm going to show that. Let's say that y, let's say that h of x is equal to f of x over g of x. Is everybody cool with this? We can rewrite this as f of x times 1 over g of x, right? Breaking this up, we see that we've got the product of 2 different things here, right? So let's take and apply the product rule now. D dx of f of x times 1 over g of x is going to give us f prime of x over g of x plus, let me write it a different way, less sloppily. D dx of f of x g of x is equal to 1 over g of x times the d of x of f of x plus f of x times the d of x of 1 over g of x now notice 1 over g of x, this is the chain rule, right? Apply that there. So taking a little segue and realizing that I write crooked as hell on a board. Got d dx of 1 over g of x. Well, this is going to be like d dx, my mistake, d du of 1 over u times d dx of g of x. Everybody agree? So we're going to get 1 over u squared times g prime, or g prime over g squared. Right? So coming back up here then, we can rewrite what's over here as 1 over g of x times f prime of x plus f of x times g prime over g squared of x. Yeah. Now, in order to be able to add these together under one fraction, we need to multiply this by g of x over g of x. Agreed? Yeah. So when we do that, we get g of x over g of x squared, and the rest is just algebra, straight arithmetic. Yeah. So as I said, you can apply just the product rule directly and get it that way. Having said that, 8 minutes. Do we have enough time to go through a couple more of these? Let's go over this one. This is a good one. All right. We're given that f of x, which we're going to represent as h of x in this case, given that this thing is our f of x. So that's going to be 3x minus 1 over x squared plus 3, that quantity squared. Now we can rewrite f of u as u squared. We can rewrite u as 3x minus 1 over x squared plus 3. Use different colors so everything's easy to read. So the derivative of f of u is going to be equal to 2u. The derivative of u is going to be x squared plus 3, that quantity times 3 minus the quantity 3x minus 1 times 2x, all divided by x squared plus 3 squared. This is b prime. So we find that working everything out, we've got u primed here. Same thing. We've got 2u here. Same idea. And now from here, it's just algebra. Make sense to everyone? Sweet. All right, so as a quick review of all of our different rules, we've got the constant rule, which says the derivative of a constant is 0. We've got the constant multiple rule, which says that the derivative of c times a function is just c times the derivative of that function. We've got the sum of difference rule, which says that the derivative of f plus g is going to be the derivative of f plus the derivative of g. Similarly, for subtraction, the product rule tells us that the derivative of f times g is going to be the derivative of f times g plus g times the derivative of f. I said that backwards. I just said the same thing twice. It's going to be, like they say, f times the derivative of g plus g times the derivative of that. And then after that, the quotient rule. High D low, low D high, all over the sum or the square of what's below. The power rules. And of course, everyone's favorite chain rule. Having said that, I will let y'all go. Anyone has any questions? I'll stick around. On the exam, I believe I put 12. I believe. Yes, on all of chapter 1. Yeah, I'd have to go back and actually look to see what like how many problems I put on the exam, but I seem to remember 12. Any other questions?
Is there a question of the week?
Anytime there's an exam, I'm not going to give you all a question of the week because the exam effectively does the same thing. Yeah, if y'all have any other questions, stick around. It's posted already.
It's posted
yeah,
already?
yeah.
Until when?
Until Sunday night at midnight. You'll have 90 minutes to take it. And you'll have 90 minutes to take it.
Okay.
There's an announcement on Blackboard that like details it all out. But it posted the same time class started today. And will be available to you all until Sunday, like I said, at midnight. You have 90 minutes to take it. There is a lock browser feature. So you're going to have to download the block browser thing.
Oh, gotcha.
If you close out of it before you're done, it just ends the exam for you. Yeah. And I'm pretty sure, like I said, I didn't go way overboard with questions like I sometimes do, not on this exam. Because exams, the point of it is just to see what you know, what you don't know. And we'll give you all a hint on the exam. One of the problems uses a derivative. If you catch it, it's one of the limit problems. It'll make the problem that fast. But yeah.
And which homework did you say we get extra credit if we did?
Week 4, part 1. And I